it is autonomous gardening robot. Okay, while the team is setting up, I want to mention to all 381, 441 students that we have a sign-in sheet going around. Make sure you sign in your name. If you're in the 381, 441 class. All right, with that, yeah, go ahead.
Hello everyone, my name is Adam Zaire. These are my teammates Peter, Robert, and Khan. And together we created the autonomous gardening robot. So when we looked at gardening, we kind of split it into two categories, and that's gardening for relaxation, and that's like someone who finds passion in doing it, and then gardening for yield, and that was our focus with this project. So the pros of that type of gardening is sustainability, and it's organic because you know exactly what you're putting into your vegetables that you're growing. But the cons are that it can be seen as backbreaking work, it's dirty, and it's time consuming. So our project kind of served to fix these issues. So the autonomous gardening robot navigates a plot, plants a seed, and then maintains the garden until the user is ready to harvest. So the fact that we're using a robotic vehicle eliminates the backbreaking work aspect, and the automation and set it and forget it type properties eliminate the time constraint. So the project itself can be split into three main modules, and that's mobility, the interactor, and navigation. And so Robert will go ahead and explain a little bit more in detail about mobility.
All right, and so starting off, the overall structure of the vehicle is in the configuration of a gantry. The rationale behind that is that the vehicle would be able to straddle the growing plants while not requiring a whole lot of excess room off to the side. The vehicle is 2 foot by 2 foot in terms of its actual layout and 3 feet tall. The benefit with this design is that it can actually be scaled up to any arbitrary size. You can think of the use in a medium-sized commercial plot, such as like a strawberry field, where it's not quite large enough to justify having combines and other large equipment. As far as the overall structure, the vehicle is comprised of aluminum that's both welded and riveted. The front tires are pneumatic with the use case of having to be in a soft soil plot. The rear wheels, unfortunately, are casters. We originally went with pneumatic casters. However, due to the size and weight of them, it was going to make the vehicle much too heavy and much too cumbersome. And we did have excess power with the front drive wheels that dragging the rear casters through the dirt was actually problematic, and so we could get away. Along with that, we do use differential steering, so turning the front wheels in different directions to actually perform the in-place steering gives us some pretty tight maneuverability in the small plot. And then overall, the printer is suspended, the rationale behind that being that with a gantry system, as it goes over uneven terrain, the vehicle itself is going to flex, and we didn't want anything binding up. So suspending it would take the pressure off of the 3D printer component. And so this video here is us out in front of the Arboretum testing the dynamics of manual control on the vehicle to get a feel for overall how the sensitivity of the motors worked, the overall behavior of how it would come to a stop, and the actual turning ability of the vehicle. This was all performed with our mobile application.
So the interactive component has two main tasks. That's watering and seeding the plants. So at the bottom here, you can see two syringes. One of them is connected to a water pump, and of course that would just squirt out water to water the plant, and the other is connected to a vacuum pump. So the idea behind that is that it will use suction to pick up the seed and stab it into the ground to plant it. So the overall design, like we said, is based off a 3D printer. So we'll move left and right using stepper motors and a rubber belt. We'll move up and down using 2 stepper motors and 2 threaded rods. And forward and back is just the vehicle itself moving. So here we have a demo of the hole punching. And so before it actually plants a seed, it will have to punch a hole in the ground. And the reason we do that is because we found out if you just tried to plant the seed would just fall off because the suction's not strong enough. So we just pre-punch a hole down. And you can see here the thread rods moving the Z-axis up and down on the mechanism. So here you can see, if you can see it at the tip of the syringe is a seed, a radish seed, and this is just a demo of it moving into the ground. It's a little slow, so we sped it up a little bit, but yeah.
This is a cut that takes us to the next level.
So,
Yeah, so after the seed's planted, then we go ahead and water it, and this is just showing the water pump turning on and actually watering that. And the next one is, like after, let's say the row has been planted and it's growing, so this is maintaining it. And so you'll see it actually water and then actually adjust what we're calling the interactor head in order to get a better, to spread the water around.
Alright, so for navigation, the core of the navigation was a low-cost system composed of two Logitech webcams. And the idea of it is that it has two different planes of view. So you can see them on the system right here, one's facing forward, one's facing back. And this will get two images that you'll be able to use to triangulate the position within the area. And using this position, we can start to schedule tasks and perform operations. So we have this task scheduling system where we queue up tasks, and these tasks are enrolled into smaller steps, like say move to this place or pick up a seed or plant a seed. And so by doing this, we're able to schedule and handle a great deal of tasks whenever we need them to be performed. And with all this in mind, we can move to a live demo showing some of the capabilities of what the system is. So let me start the demo. All right. So here we're doing a sort of conceptual planting and seeding of the system. As you can see right here, it overshot its value because the system was not calibrated to work inside. This system works much better outside because these colored markers are going to be shaded better, and we'll have a much larger area, so it'll have less issues with field of view. In these smaller confined areas, we have these issues where this system can't see what's inside the area because it won't get a ball within the frame. And so using that, we have this system that's able to move around and move to wherever it needs to. And using manual control, which I can show on this app, we can get it to be much more mobile and move to wherever we need to go. It is a little aggressive, so
Start doing donuts.
that is only at 50% speed, mind you.
Grace?
Do you
So,
want to get into the next one? Yeah. So just a quick overview of the budget.
Yeah, as far as the budget goes, we had started off with a little over $900 in the budget. For motors and drivers, that came out to about $200. Initially, we had ordered a set of motor drivers. They were rather inexpensive, and the moment we hooked them up, some of the actual electrical tracings on the board actually flashed and were shorted out. So we had to buy another set. Pumps and tubing, 120 between the vacuum pumps, going through a couple of iterations of water pumps that would work. Wheels and vehicle frame came in under budget from what we were initially anticipating. I was able to be a little bit frugal and recycle a lot of the structural material from other items so that we could avoid having to actually buy everything from scratch. And then the miscellaneous electronics include things like the Arduinos, the stepper motor controllers, the Raspberry Pi, the battery packs, and the miscellaneous electronics. So all total, we came in at $800 under budget. And so now, any questions?
Your plot in the algorithm.
Oh, yes, we implemented this actually here at the Arboretum. And so we use the community garden. They were kind enough to lend us one for the 2 semesters. And so actually, if you go there right now, we have kind of 2 rows set up. They're radish and kale growing in there.
all the videos you saw were taken in those plots, and we were watering the plants that we were growing.
Quick question.
Thank you.
So you guys are using the balls to enclose the area like in a garden?
It forms a sort of pen that
Yeah.
so we place them on the edges of the garden.
And so have you guys been able to like go down a row and then turn, like, well, that would be the eventual, so, like, it would be able to do a row, come out, turn, and then come down another row, turn, come?
Yes, to be able to operate within the confines of the plot completely autonomously. The system uses a bit of trigonometry in terms of the angles between the balls that are being viewed, as well as the apparent size in terms of pixels. So the system does require calibration ahead of time, knowing as far as where they're placed, as well as how large the balls should be at a certain distance. But once you've calibrated the system, you can do math to actually triangulate your position within the plot.
So if you were calibrated, like a good calibration, do you know roughly what your accuracy is, like over the plot? Are you within 6 inches of kind of the line you want to be on, something like that?
The navigation system was built around the size of a minimum square for the, so we're using what's called A-star navigation. And this is, you can see this used in video games a lot, and it's used within grids. So in this case, we used a grid of about 2 inches per square. So that's the minimum unit size of this navigation system.
So it's plus or minus 2 inches?
About, yes.
Wow.
And because of the margins, we were able to make that fairly accurate.
Can we have a radish?
Yeah, where's the radishes?
They're still at the plot. You're welcome to.
All right.
One more question.
Can it go uphill?
Yes, the demo you saw running, that was running at very low power. When you saw it move very quickly, that was at 50%, and it has another headroom about 75%, but we limit it so that it doesn't damage itself. So it's got plenty of power that we kept just in case.
Have you measured the current on those motors right there? Because power is current, not voltage. Because if you're starting to go uphill, your current's going to go up. It's not necessarily how much you feed into it. Have you guys looked at that, going uphill?
Well, so we've been testing it with 12 volts. We do have it set up to where we can actually go up to 24 volts to actually
Lower
get
the current.
more out of the motors. But at this point, we were being modest in terms of testing. We didn't want to burn anything out or have any accidents with it also being a metal frame. So we were operating it at 12 volts. But we do have the headroom to actually set that up to 24 volts.
Okay.
Okay, one last question. Yes.
Hi guys, I think it's such a fantastic idea. How did you guys come up with it?
You like to eat?
Well, it was a discussion amongst the team initially. Initially, we had 2 other group members that, you know, everyone was throwing in ideas and we had to pull.
The funny aspect is she was involved with the plan of the project.
Well, you do know that today in farming, they have GPS on their tractors, and they actually put a piece of fertilizer at the end of the season for exactly where that next seed's going to go next year. That's already technology on the tractors.
But that's with bigger.
Big, I mean large.
Yeah, so one limitation we had is for so GPS units that were within the realm of our budget,
Oh, yeah.
the accuracy could only tell us you're in the plot, you're not in the plot.
Yeah.
We couldn't get accuracy enough to actually do anything useful within the plot, so we had to come up with some other type of positioning system for within the boundaries.
These are $20 cameras and
like the walls.
$35 computers.
That's brilliant. Simple.
Very good.
Real quick,
One
so
last.
agriculture robotics and so forth, it's the #1 fastest growing, call it VC or investment spend for robotics in the world today. So not only, things that plant, but things that pick. We just finished a big job with a customer in New Zealand, and they're flying drones to do all kinds of multispectral analysis of the crops, and mostly things like kiwis and that kind of junk. And but this is the biggest growth area for robotics in the world today for venture capital investment and R&D. Everybody thinks it's autonomous vehicles like cars, but it's not. It's agricultural robots.
Because we don't like food.
Well,
You've been there before.